Hello everyone. In this video, let us learn the overall design aspects of a transformer. So we will dissect the transformer into different portions and we will learn how to design each and how to integrate everything. The first one is code. Let us first learn how to design a code. When you talk about the core, the coils are also directly linked into it because the coils are the one which is going to surround the core, or either the core will be surrounding the coil or the coil will be surrounding the core. So both are actually interlinked. So we have to also look into what type of coil we are using to decide on what type of core we require. So first we learn what are the types of coils available. Now we know that there are two common types of coils which we already dealt with are rectangular coils, another one is circular coils. So when you are having a rectangular coils, that means when you require rectangular coils to be used, we'll go for a rectangular code. When we require circular coils, we'll go for a circular code, or we'll also move to a stepped code in quite short time. Now we all know that what is rectangular code, which I already discussed in the introduction class. So I am directly moving on to the square code. Now suppose if we are going for a if you are opting for a circular coil, then the core we required will be a squared code. Now the diagram which is shown here, the outer coil is the outer circle that is representing the circular coil, and square box with shaded lines represents the squared code. Now let us take the side of the square as A, small a, and D stands for either the diameter of the circle or the diagonal of your square. Now we usually call this circle as a circumscribing circle because this circle is surrounding a square code. Okay. Now we will understand the basic expressions related to this circular this square code. Now from the diagram it is very clear that if you consider this portion as a this portion I'm shading it here, if you consider this portion as a right angle triangle, you can easily find out the expression from Pythagoras theorem, that is d square is equal to sum of the square of two sides. Each square each side is a, so it is a square plus a square, or in short I can write it a square is equal to it is d square divided by 2. So finding out what is the gross iron area. Gross iron area includes the square section area. So gross iron area AGI is equal to square, the area of the square is side square, that is a square. If I write in terms of diameter, it is d square by 2 from this expression. Next, if you have the gross iron area, you can find out what is the net iron area using your stacking factor. If I take stacking factor is equal to 0.9, then I'll get AI equal to 0.9 into d square divided by 2. When you divide it by 2, you'll get AI equal to 0.45 d square. We'll consider few ratios. One is ratio of what is net iron area to circumscribing circle area. Circumscribing circle area is pi r square, or it is pi d square by 4. That is what given in your denominator. It is pi d square by 4. And AI value just now found it out, it is 0.45 d square. Substituted, you will get a number 0.57. Similarly, a ratio relating AGI and circumscribing circle area, you will get a number 0.63. With this, we can find it out what is the core area factor Kc, which is what is the net core area out of the square of the circumscribing circle diameter, that is AI divided by d square, that is equal to 0.45. Now all these values are pertaining to your square code. Now I already told you the disadvantage in this squared code is the core is underutilized in this model because you can see that there are so many portions which are left unused. So the next what we are going to do is I am going to make more utilization of the space by converting the square into a stepped shape, and that diagram is shown in your next one. So this is called a stepped core, or we also call it as cruciform core. This is cruciform core. Now let us find out the gross iron area for this shape. In the previous case it was a square, so directly we wrote it as a square, that is product of two sides. But here we have three different sections, so we will divide each into one section, that is section 1, this is section 2, and section 3. We'll find out the area of each section, and when we add it, we'll get the answer for AGI. If I consider second section, that is this one rectangular, you know what is this size? It is A, okay, and this side is B, and so the area of second portion is nothing but it is A into B, okay. Next, uh, if we consider the section 1, the section 1, this length is nothing but what it is, B, okay, this length is B. So what about this length? So this full length is A, this is B. So it is A minus B, that will be these two portions, and each portion will be half. So this portion will be, it is A minus B divided by 2. Similarly, this portion is also equivalent to A minus B divided by 2. So what will be the area of section 1 and 3? Section 1 area will be nothing but it is A minus B divided by 2 into B. Similarly, for section 3 also you will be getting A minus B by 2 into B. So when you add all these three and simplify, you will be getting AGI is equal to AB plus B into A minus B. Now, we'll proceed. We can easily find out what is the value of A and B in terms of your trigonometric identities. Now consider this small right angle triangle, okay, with an angle theta, and this length is A and this length is B. I have redrawn it here. What about this? We know that the diameter of the circle is D. So this line is nothing but the diameter of the circle. So this is nothing but D. I write it as D. Now, if we find it out, what is sine theta and cos theta? So sine theta is equal to opposite by hypotenuse, it is B divided by D. Similarly, cos theta is equal to adjacent divided by hypotenuse, it is A divided by D. Now when you rearrange this, what will you get? You will get B is equal to D times sin theta, this expression, and from this D equal to A is equal to D times cos theta, this expression. Now from this triangle we have got the expression for A and B. Substitute this in this equation and simplify and rearrange it. You will get the final answer as AGI is equal to D square into sine 2 theta minus sine square into theta. So this AGI is nothing but area. So if I want to make use of a maximum area, so A is missing here. So if I want to, what is our aim of using step to core? I want to use maximum area that should not be left out free. So if I want maximum area, you know that mathematical condition is either for a maximum or minimum objective function, the first differentiative has to be equated to 0. So I am going to differentiate this AGI with respect to the variable theta and equate it to 0. So when I differentiate this and equate it to 0, that means I have to differentiate this with respect to theta, and then I have to equate it to 0, and when I solve it I'll be getting the value of theta as 31.72, or in terms of degree 31 degree 42 second. Now when I substitute this theta value in this AGI, I'll be getting the expression for AGI as 0.618 into d square. So in your square core, we didn't face this much of problem. We were able to directly get the answer like this, AGI equal to d square by 2. But here we have to do this much of equation steps to find out what is AGI, that is equal to 0.618 d square, and the rest of the steps are similar. Find out AI in term by using the constant Ki. You will get this expression. You can find out the ratio relating AI with circumscribing circle area and AGI with circumscribing circle area. You will find these values, and finally the core area factor. Why do we find all these values? All these ratios? I have listed out the ratio value of a specified ratio value like this. This is a ratio which tells you the ratio between AGI, the gross iron area, divided by pi d square by 4, that is circumscribing circle area. That means this factor tells you out of the total circle area how much amount of iron is actually utilized. Now just compare whatever values we have got, okay, with all these values. So let me take this in terms of percentage. If I take in terms of percentage, what it is 64 percentage, okay, this is 79 percentage, 84 percentage, and finally it is 87 percentage. So what do we infer from this table? Suppose if you are using a squared code for a circular coil, the use percentage use is only 64 percentage of your iron. So remaining percentage are left are yearly not utilized. It is of waste. So when I change into stepped core and when I increase the stepped core from 2, 3, 4 onwards, say for example, compare these two, instead of a square core, if you are using a 4-stepped core, the percentage usage of iron is raised from 64 percentage to 87 percentage. So this tells you that a stepped core will help you in more utilization of your iron part. The second one is design of yoke. So let us learn how to design a yoke. You all know that this transformer more or less looks like rectangle in some or other parts, right? So you know how to find a rectangle area, or how to find out the parameters of rectangle. There are only two parameters of rectangle. One is length, another one is width or breadth. So similarly, our transformer also, we are will be more concerned with finding out the height and depth of your each part. Now, if you take a yoke separately, we should know what is the height of the yoke and what is the depth of the yoke. So I should know what is the depth of the yoke. I am denoting it as dy, and what is the height of the yoke, hy. You all know that what is depth into height, it is nothing but area of the yoke, ay. Okay, and these are some common values. I told you know that there are some standard data book available for manufacturing. So from that data book, suppose if you are you can it is taken from this data book. If you are using a hot rolled silicon steel as a transformer material, so you can assume the area of the yoke as 15 to 25 percentage more than of your AGI. If you are using a cold rolled grain oriented steel, we'll call it a CRGO steel, you can assume the area of the yoke and area of the core as same. If you are using the squared or stepped core, the depth of the yoke will be equal to width of the largest stamping. So what do we mean by stamping? I told you that it is nothing but the laminations which we use it for manufacturing the transformer. Why do we use the word like largest stamping? In a stepped core, okay, in a stepped core, if you see this, if you are having a single core like this width will be your stamping width. Okay, suppose instead of square core, if you are using a steps like this, so we cannot say that all the portions are having same width. So what in that case there are so many different widths available in this diagram. So which one to take? So in that case we have to take the largest stamping and we have to consider the width of that largest stamping. Okay. So for square or depth core, whichever is the largest stamping, I am going to consider that as the depth of the yoke. We usually denote the width of the largest stamping with the letter A. And third one is window dimensions. Window dimension nothing but you know what is a window. If you consider this is consider a single phase transformer, okay, the center portion is called as the window. This portion is window, and window is nothing but made up of two things. One is width, another one is height. So height of the window and width of the window, that is equal to what area of the window. Usually we cannot directly find we cannot easily find out the height and width as such. So in any cases we have to assume one factor. There might be some conditions where we have to assume one factor. So in that case they are given a standard ratio called HW and WW as 2 to 4. What do you mean by that? Say for example, if I take HW divided by WW equal to 2, that means HW, height of the window, should be equal to 2 times width of the window. This is the assumption. So 2 to 4 is a standard range. So there are infinite number of values you can take between these two numbers. So if I assume it as 2, what is the relation I'm getting? HW equal 2 times WW. Suppose if you are able to find the width of the window, then you can directly take twice the width of the window as the height of the window, or the vice versa. Okay, that's it about your window dimension. So keep it in mind, since this window is carrying the windings, there is a chance that it gets affected by the leakage reactance. So in that case, that's why they have given a range of 2 to 4. You can adjust the height of the window as well as the width of the window so that the leakage reactance is also taken into account. The next one is design of windings. Now you all know that we have two types of windings. One is primary winding and another one is secondary winding. We have mentioned it as one high voltage winding and one low voltage winding. Now when you are about to design the windings, you should keep in mind what is the number of turns required to number of turns required for the primary and the secondary, and what is the area of the cross section of the conductors required for the winding. Now you have to start with the machine rating, that is here it is Q, and you have to also take into account ET, that is voltage per turn. Why? Because what is when by voltage per turn, we all know voltage per turn ET is nothing but, as the name tells you, it is voltage per turn. Suppose if you consider it as a primary, then it is primary voltage divided by primary turn. Or if you are considering it as secondary, it is secondary voltage divided by secondary turn. So from this, you can easily find it out what is the primary turn and secondary turn. So TP will be equal to VP by ET. TS is equal to VS divided by ET, obtained from this equation. Now, to proceed with the current density, because I told you two things. One is number of turns, that we have got the formula. Second one is we should know what is the area of the cross section of conductors. If we want to find out the area of the cross section of conductors, as usual, we have to assume a standard current density value. So let us find it out what the delta P should be and what the delta S should be. That is current density in primary and secondary value should be. Once we find out these two, that is delta P and delta S, from that we can easily find out the area of the cross section of conductors, because current density is current divided by area. So for that, let us assume UP as the volume of the primary conductor. This is volume meter cube, and US as volume of the secondary conductor. If I assume the total volume as constant, then total volume is sum of UP and US. Let me take it as UT, total volume. Okay. Now, what is the copper loss in primary? I square R loss in primary. That is IP square into RP. Okay. You know what is IP? I told you the current density formula, delta is equal to current density equal to current divided by area. So if you consider primary side, it is delta P is equal to IP divided by AP. Similarly, you can also write it as delta S is equal to IS divided by AS. Now from that I can replace IP by delta IP into AP. Similarly, you know the basic formula for resistance, it is rho L divided by AP. Substitute it and group it, you will get this expression. Similarly, you can find it out the expression for I square loss in secondary, and that you will be getting rho into delta S square into US. Now what is total copper loss? Total copper loss is copper loss in primary and copper loss in secondary. So when you add these two, you will get this answer. You can have either UP, both, you can either have both the volume in terms of primary or in terms of secondary. So either you can replace this US or you can replace UP. Suppose if I replace UP, US, what is US is nothing but US is equal to, it is UT minus UP. So now if you see that this copper loss consists of only the primary side UP, primary side value UP. Now as usual, if I want this total copper loss to be minimum, mathematically the first derivative has to be 0. So either if you take it all in terms of UP, differentiate with respect to UP and equate to 0, or if you are writing it in terms of US, differentiate with respect to US and equate to 0. Once you simplify that differentiation term, you will be getting this expression delta P equal to delta S. So from this it is clear that if you want the if you want the copper loss to be minimum in this transformer, then you have to choose the current density in such a way the current density in the primary winding and the current density in secondary winding should be equal. So hereafter, this is the reason, okay, this is the reason in our output equation, when we were about to derive the output equation, we assumed delta P equal to delta S is equal to delta. Okay, this is the reason why we assumed it as delta in that point. Okay, and these are some standard values for your current density, considering the type of transformers for distribution small power transformers, and if you're going for a large power transformers, based on the method of cooling, the value for delta will change. This is a standard value. Either they will give in the question, or you have to remember this and you have to use it whenever it is necessary. And this tells you about the type of windings, high voltage winding and low voltage winding. If you are going for high voltage winding, you can pick up any one among these type of conductors, and even you can also choose based on your rating, machine rating, voltage rating and kVA rating. And if it is a low voltage winding, you can choose any one among these two coils. So and finally, we will stop our discussion with this overall dimensions of the transformer. So far we have discussed everything in detail in parts. Now we will combine everything and we will find it out what is the overall dimensions of the transformer. Now I'm showing a diagram here. This is nothing but a front view of your transformer. Assume that some transformer is you are standing before a transformer. So whatever view you have, that is called as front view. And if you view this transformer from the top like this, and that is called as top view, and that diagram is shown here. Here, let me tell you what are the terminologies used here. This W stands for the width of the transformer. Okay, this is overall width. You can see in this arrow mark. This is overall width of the transformer. Similarly, this H is your overall height of the transformer. So, if you take this as a transformer, this W is overall width, and this WH is overall height. Okay, and what is that D stands for? I told you from this diagram. If you see, this D stands for, this is center to center distance. This is center of this limb, and this is center of this limb. This is center to center distance of two adjacent limbs. This is limb 1. Okay, this is limb 1 and this is limb 2. And center to center distance is called as capital D. And what does the D small d stands for? As usual, the small d is nothing but it is the diameter of the, see, this is the small d is nothing but from this side to this side. So this diameter of the circumscribing circle. Okay, and when you come here, you all know what is this portion. This portion is nothing but the one which I'm highlighting here is nothing but your window, correct? This is window, and this is height of the window HW, and this is width of the window WW. So this is window, this is width of the window, and this is height of the window. The same way from the top view also you can easily find out. You cannot say the height, but you can find out the width. This is nothing but width of the window WW. Okay, and what about this? I told you the top and bottom portion are called as yoke. So this portion, this is called yoke, right? So this portion is called as height of the yoke, and this is also height of the yoke. Now with the top view, you can find out what is the depth. Suppose if we take this height and we want to find what's the depth in this range. So this will be your depth of the yoke. Okay. And what do you mean by A? I told you A is nothing but width of the largest stamping. Now if you see dy is nothing but it is equivalent to this diameter, correct? So this is nothing but the width of the largest stamping. So you can directly write dy is equal to A. So these are terminologies or notations we are using for overall dimensions. Now from this you can easily find out this formula. Now look at this H. One minute. Change. From this diagram, it is clear that when you look at this portion, okay, what is the relation you're getting? H is equal to HW plus HY plus HY. So it is equal to H is equal to HW plus 2 times HY. This one. H is equal to HW plus 2 times HY. Now look at this portion, these three portions. What you're getting, it is D is equal to, capital D is equal to WW, and this portion is D by 2 and this portion is D by 2. So what will you get? It is D is equal to WW plus D by 2 by D by plus D by 2. So when you add, what will you get? It is D equal to WW plus D, and that is this equation. Okay, and what about dy? When you relate these two, you'll get dy is equal to width of the largest stamping, that is dy is equal to a. And when you talk this w in terms of d and a, so look at these two diagram. This is w, no, this is from this end, this is w. So w is nothing but this is d, okay, and this portion is a by 2 and this portion is a by 2. So it is w equal to d plus a by 2 plus a by 2. That becomes d is w is equal to d plus a. And similarly, you can find out all possible expressions from this dimensions. So for problem solving, you will be given a design question where they will be giving you the rating of the transformer, power rating of transformer, and voltage level of primary and secondary winding along with the frequency. Now you have to make assumptions if there is no explicit value given in the question. So make assumptions wherever necessary, and finally you will be finding out what is the value of H, what is the value of height of the window, width of the window, height, overall height of the transformer, overall width of the transformer, what is the width of the largest stamping. So like all these factors we will be determining from in the given problem. Okay. Thank you.